This video looks at the compaction process. Compaction is carried out on a soil and involves forcing some of the air out of the voids by applying a static or static and dynamic pressure. The compaction causes the soil particles to move closer together, expelling some of the air in the voids in the process. This results in a more compact soil mass which has more strength and bearing capacity and is less sensitive to water. Bearing capacity is the ability of the soil to support a vertical load without deformation, without settling. In a compacted soil, there are more connections, as shown in the red dots on this picture, between the soil particles, so providing better support of the load and a higher strength, which lessens the settlement of the soil under load. The expulsion of some of the air results in a reduction in the volume of the voids between the soil particles. This causes the volume of the soil mass to reduce, resulting in an increase in the soil density. The lower void volume means the voids will retain less water when the soil is saturated, meaning that the soil water content is lower than it would be in an uncompacted state, and the soil is less prone to softening that would have been caused by the higher water content. You'll recall the liquid limit and the plastic limit that we looked at in the previous slides. In other words, the soil has less sensitivity to water. Compaction can be achieved by one or a combination of the following methods. Impact, which is a short, sharp application of force on a soil, like a blow. This is effective on fine soils, especially clays, if they are confined to prevent the clay squishing around the sides of the impacting object, but it's not all that effective on coarse soils. Pressure is a constant static weight on the soil mass. This is also effective on fine soils, but not so much on coarse soils. Vibration, which is the shaking of the soil particles to arrange them into a more compact arrangement. This is effective on coarse soils where the soil particles are not bound by cohesion and can be arranged into a more compact arrangement by vibration. Lastly, kneading, which is the manipulation of the soil to rearrange the soil particles into a more compact mass. This method works well with all soil types, but is particularly effective for the fine soils, although it usually only affects the top part of the surface. So compactors are plant and equipment specifically designed to hasten the natural compaction process by applying additional force on the soil mass to decrease pore pressure and so increase the soil density. They may be steel rollers, Sheepfoot rollers, or pneumatic tire rollers. Steel and Sheepfoot rollers can have vibration devices that vibrate the drums, so producing both pressure and vibration. Steel rollers in vibration mode are usually used for the initial compaction of coarse soils. In static mode, that is without vibration, they are used in the final compaction and surface tightening for all soils. Sheepfoot rollers are usually used for the primary compaction of fine soils. Pneumatic tired rollers, or PTRs, are usually used to tighten up the surface of both fine and coarse soils. So let's look at each one of those in turn. So steel rollers have rollers on one or both axles. These rollers apply a constant pressure to the soil surface as the roller passes over it, resulting in soil particles being forced into the voids, and so compacting the soil. The drums can be filled with water or sand to increase the weight of the roller, and hence increase the pressure it applies to the soil mass. One or both drums are often fitted with a vibrating device that vibrates the whole drum. This means that the roller can provide both impact and vibration when in that mode, in addition to the pressure to aid compaction. The vibration mode can be turned off to provide just static weight. In vibrating mode, the roller is very effective at compacting sands and gravels. The vibration and weight of the roller cause the sand or gravel particles to move into a denser structure. However, the vibration mode is not suitable for some fine soils as it can create liquefaction. Care also needs to be taken to avoid overcompacting the soil, especially in vibrating mode, as overcompaction can break the soil particles, or it can vibrate the surface particles out of the soil mass and actually loosen up the surface. Therefore, the last few passes of a roller are in static mode to tighten up the surface. A sheepfoot roller is also known as a tamping, padfoot, or clubfoot roller, and it has pads or feet on the roller. These pads or feet concentrate pressure on the ground and compact the soil both vertically and horizontally, as shown in the diagram. These rollers provide the best initial compaction of clays and silts, as the feet are able to penetrate the soil and compact in both vertical and horizontal directions. However, the feet can usually not penetrate a coarse soil mass and are not much use for these types of soils. The imprints from the roller get shallower as the soil gets more compact. When there are just shallow imprints, then the soil is compacted. This photo shows a sheepfoot roller. Note that the rollers have knobs on the rollers. This roller also has a blade at the front which allows it to push the soil out into a thin layer, which removes the need for a separate bulldozer to do so. A pneumatic tired roller, or PTR, has multiple tires on each axle. Tires are flexible and tend to knead the soil surface as the roller passes over. This action can tighten up the surface, enabling it to better resist loadings, especially horizontal loadings such as those from vehicles accelerating or braking on them. It also makes the surface of fine soils more impermeable, which prevents water entering and softening the soil mass. PTRs are usually only used at the end of the compaction process in secondary compaction, when the final formation level and shape have been achieved. So let's look at the compaction process in a little bit more detail. The object of the compaction process is to compact the soil to a specific density at which we know it will have the required bearing capacity based on the lab tests we did on the soil. So we need to measure the dry density during the compaction process while we're on site. The measurement of the density in the field is often undertaken with a nuclear densometer. This photo shows a nuclear densometer in action. The yellow box contains the measuring equipment and a small amount of radioactive material. The handle is the top of a probe which is pushed into the ground. The probe contains a small amount of radioactive material at the end, which emits gamma radiation, as shown in the diagram. The box measures the amount of gamma radiation that gets through the soil back to the box. The instrument correlates the gamma radiation received with the density and provides a reading on the wet density of the soil. The water content of the material being tested affects the density reading, so there is a second radioactive source under the control panel, which is used to measure the water content of the material. The instrument calculates the dry density by adjusting the wet density reading. It is directly measured by the water content. So the nuclear densometer gives you an estimate of the dry density and the moisture content. So how do we use that? So compaction needs to be achieved using the least number of compaction passes. If there are too many passes, then the compactor could start crushing coarse soil particles, especially if it is in vibration mode. However, too few passes mean that the soil is not properly compacted. So we need to determine how many passes a particular roller needs to compact the soil to its maximum dry density. So we carry out what's called a plateau test at the start of the earthworks process to calibrate the rollers and soil that we're using. The plateau test starts with measuring the density of the soil layer before compaction using a nuclear densometer. The roller that you're going to use will then undertake the primary compaction of the soil with one pass over the soil layer, and the dry density is again measured. This process then continues with the density being measured after each pass and the results being recorded on a graph of the number of passes along the horizontal axis versus the dry density on the vertical axis. The graph normally looks like this after a few passes. Note that the effectiveness of primary compaction levels off into a kind of plateau, where additional passes do not result in any significant increases in dry density. So you can see between the third and the fourth passes, you're not actually achieving much extra dry density. At this point, the operator then knows that the number of passes required to get to that plateau and knows not to use primary compaction after that. The test area is then compacted using steel rollers in static mode or PTR in a secondary compaction process, and the density is once again measured, yielding a curve like this. This different type of rolling yields an initial increase in dry density, but the curve levels off to another plateau after a few passes. So you can see after the second pass in the secondary compaction, you're pretty well plateaued, you leveled off. This is the point where you stop compacting, as you have achieved as good a dry density as you can. This process gives you the number of passes required for each type of roller, and the compaction process can then proceed. You would check the final density of each layer, but you do not need to redo the test unless you're using a different soil or you are not getting the required density you need.